In 1995, the Hubble Space Telescope dazzled us all by producing the first of its deep field images. Instead of aiming for a particularly interesting object, astronomers intentionally pointed the telescope at the darkest, emptiest, least interesting part of the sky they could find, opened the shutter, and waited. Over the course of 10 days, astronomers continued taking long exposures of the same completely unremarkable part of the sky. What they saw in the final image was truly astonishing. In that tiny pinprick region of the sky, only as wide across as the head of a pin held at arm's length, there were nearly 3,000 galaxies. The cosmos is teeming with galaxies, vast, swirling collections of millions or billions of stars. Current estimates suggest there may be as many as 2 trillion in our observable universe. But observations of distant galaxies give us more than just an awe-inspiring view. They allow us to trace the history of structure in the universe, and even give us insight into the basic building blocks of physics. And sometimes, they present us with new mysteries we never saw coming. When the new space telescope JWST first started sending back its images of the most distant galaxies ever seen, astronomers were elated, both for the massive success of an incredibly ambitious project and for the fact that the galaxies completely defied expectations. These galaxies are so distant that their light has been traveling for more than 13 billion years. We are seeing them as they were only a few 100 million years after the Big Bang. We didn't expect them to look like modern galaxies exactly. We expected them to be smaller and dimmer. What surprised everyone was that they were apparently impossibly massive. They seemed to have grown up way too fast. We think we understand the basics of galaxy formation in general. In the early universe, the first galaxies were born when clumps of matter began to fall together under their own gravity. These clumps were a mix of hydrogen and helium and something we still don't understand: dark matter. While the gas provided the ingredients for stars, the dark matter provided extra gravity to pull everything together. The problem is, even accounting for the dark matter, it's still not clear exactly how those earliest galaxies got so big and bright in such a short time. When we compare our observations to our computer models of galaxy formation, it seems to tell us that something isn't matching up. At the moment, the jury is still out on how to explain those bright young galaxies. Some have suggested we need to rethink the Big Bang theory from the ground up. But there's a less extreme possibility. Maybe the real problem is that galaxies are just complicated, and our computer models are built on observations of modern galaxies with totally different backstories. Across most of cosmic history, galaxies have formed primarily through unimaginable violence. Large galaxies are cannibals, constantly consuming and shredding any smaller galaxy or star cluster unlucky enough to get caught in their gravitational well. Even as the universe on the whole is expanding and galaxies on average are getting farther apart, since most galaxies form in groups or clusters in the first place, a lot of galaxies end up tearing apart and merging with their neighbors. We can see evidence of this kind of cosmic cannibalism in our own Milky Way. Careful observations, especially with the Gaia satellite, show us streams of stars crisscrossing the sky. These stellar streams are the remnants of small galaxies and globular clusters that have been pulled apart like taffy in the gravitational field of the Milky Way billions of years ago.
Galaxies are fairly diffuse objects. They're large distances between the stars in a galaxy. When two galaxies come close together, each one exerts a tidal force on the other, kind of like the force that the Earth exerts on the Moon or the Moon exerts on the Earth. In the case of a galaxy, that force is actually big enough relative to the gravity of the galaxy to tear material right out of it. And it can tear it into lobes that orbit a little bit faster or a little bit slower, and they gradually stretch out into this long tidal stream. It's an interesting process because it allows us to probe something that we can't necessarily see in any other way, and that is the gravity around each galaxy. And that in turn gives us insight into what the dark matter distribution is in the galaxies.
Not all galactic mergers are straightforward predation events. Sometimes the galaxies are more evenly matched. When two large galaxies collide, the result can be an incredible light show. The sudden shock of the gas of the two galaxies slamming together can cause a burst of star formation and spectacular supernovae. Meanwhile, the immense gravitational forces create long streamers of stars stretching out into the void. These kinds of cosmic train wrecks were far more common when the universe was about half its current age, somewhere around 6 billion years ago. But it can still happen. In fact, our own Milky Way is fated for just such a clash of the titans, when, in 4 billion years or so, it gets up close and personal with our massive neighbor, the Andromeda Galaxy. On a dark, clear night, at the right time of year, Andromeda is visible to the naked eye as a faint smudge below the W-shaped constellation Cassiopeia. Unlike the distant early galaxies seen by JWST, Andromeda is not moving away with the expansion of the universe. It's coming for us, at 110 kilometers a second. Good thing it's still 2.5 million light years away, for now.